What's up, guys? This is Mr. Bond. We're going to run through differentiability today. So differentiability is the idea of being able to find a derivative on a graph. Now, the word derivative is a fancy one. It just means slope at a single point. So let's just review some basic slope for a second. Here's a function, and I can draw 2 points on my function somewhere, and I could find the slope between those 2 points. That's pretty easy. That's like old stuff, right? Slope between 2 points, very basic. But in calculus, what we want to do is we want to find the slope at a single point. We want the slope of the tangent line. So imagine this point right here. You can imagine a tangent line, which means it's passing through at just that one point. And we could find more tangent lines all along our curve. So the idea of differentiability is the ability to find a derivative, and a derivative just means a slope at a single point. So the goal for today is we're going to be looking at different graphs, and we're going to get a sense of when can you find a derivative, right? When can I find the slope of a tangent line, and when can't I find the slope of a tangent line? So in order for a derivative to exist for a function, or slopes to exist for a function, 2 things have to be true. The function has to be continuous. So we already talked about continuity when we looked at holes and jumps and infinite discontinuities, so those are back in play. And also the left-hand slope has to be equal to the right-hand slope for all the x values within the domain. So if these 2 things are true, if the left-hand slope is the same as the right-hand slope, and if the function is continuous, then that means that the function is considered to be differentiable, which just means that at any given x value over the course of the function, you can find a slope at a single point. So in a perfect world, we'll be working with functions that are continuous and are differentiable, but sometimes derivatives fail to exist. The first case in which a derivative fails to exist is at any discontinuity. So bringing back our discontinuities, when we looked at standard 3, we're talking about holes, jumps, and infinite discontinuities. So if any of these occur on your graph, your function is not differentiable at those places. It's also not continuous. We already knew that it wasn't continuous. That's not new information, but now we're adding this new layer to it. We're saying that if you have a discontinuity, your graph is also not differentiable, which means you can't find the slope at that specific x value. Now let's take a look at some specific examples of places on a graph where it is continuous, but not differentiable. A corner is the first example. This is what a corner looks like. The technical definition of a corner is that the derivative from the left does not equal the derivative from the right. So remember that derivative just means slope. So if you look at the slope from the left-hand side, you can see that that blue highlighter I used there, it's clearly a positive slope when you're approaching from the left. That little red highlighter, it's clearly a negative slope from the right. So if I had a function like f of x equals the absolute value of x minus 3, you can see that it creates a corner at x equals 3. So because the slope is different on the left-hand side from the right-hand side, we say that we can't find the slope at 3 specifically, right? I wouldn't know how to create my tangent line. I wouldn't know what the slope was. Imagine trying to ride that wave, right? We wouldn't know exactly what the slope would be when we tried to turn that corner. So we say that the derivative does not exist at x equals 3 or at any corner on our graph. The next type of place on our graph where we have continuity but not differentiability is a cusp. This is what a cusp looks like. It's kind of like a fancy corner. It's very curved. The technical definition is that the derivative from the left and the right each approach positive or negative infinity. So from the left-hand side, you can see my tangent lines here. They're all negative, and they approach negative infinity or positive infinity, depending on your perspective. On the right-hand side, those are all positive slopes, and they're just slowly becoming more and more vertical, right? So my slopes are becoming vertical, and from the left, we have negative slopes. From the right, we have positive slopes. So since the slope is becoming vertical as you approach that cusp, you wouldn't be able to find the slope at that specific cusp, but your slope would be undefined. right? We know that vertical slope is undefined. So our function is not differentiable at a cusp. The last type of example of where your graph can be continuous but not differentiable is a vertical tangent. Vertical tangents are really hard to see. They look something like this, where there's just that one point where suddenly your slope is undefined for just a brief second. So we're passing along, we have negative slopes, negative slopes, negative slopes, vertical slope. On the other side, we also have negative slopes. I'm going to make them blue, though, just so that we can emphasize the two sides. They are negative slopes on both sides of this thing, but right as you approach that point that I emphasized, you suddenly have a vertical tangent line, and we know that vertical lines have undefined slope, so we can't find the slope at that one specific emphasized point on my little sketch here. So a vertical tangent, they're very tough to see when you have a big graph. Be on the lookout for places on the graph where you can clearly see it flattening out in a vertical way. That's a vertical tangent. All right, we're going to look at some logic statements here. Apparently the math budget was high enough for this video that we were able to bring some geometry back. If your function is differentiable, it also must be continuous. Conversely, if your function is continuous, it is not necessarily differentiable. Take a second for that to sink in. Let's look at the absolute value of x. We know what the graph of the absolute value of x looks like. We know that it's an absolute value function. It looks like a v. It's definitely continuous, right? You can sketch that function without lifting your pencil, but it's absolutely not differentiable at x equals 0. Why is it not differentiable at x equals 0? Because we have a corner, right? The derivative from the left and the derivative from the right do not match. Every time I say the word derivative, you should be thinking slope. The slope from the left does not match the slope from the right when we're looking at x equals 0. So we say that it is not differentiable at x equals 0. So look back at those logic statements. Look at the second one. If f of x is continuous, then it is not necessarily differentiable. So this is an example of that. It is a continuous function. I can trace it without lifting my pencil, but I cannot find the derivative at every single x value because x equals 0 is a corner. And conversely, going back to the original statement, if I was to tell you that we have a differentiable function, that you can find the slope at any x value, that does guarantee that f of x is continuous. All right, let's transition into looking at some actual questions with these things. This has been very conceptual so far. I want to actually do some practice. All right, so we have a graph that we're working with for these two questions. The first one is basically just standard 3, asking about continuity. The second one is new. It's asking about differentiability. Give this one a try and unpause when you're ready to see the solution. All right, so continuity, talking about when do I have to lift my pencil. We only have to lift our pencil once. It only happens at -1. So my interval of continuity is -infinity to -1, union -1 to infinity, and x equals -1 is a jump. Not too bad, not too bad. But now let's look at the intervals of differentiability. The question says, identify where the graph is continuous but not differentiable. Continuous but not differentiable. So we have to think about that for a second. I'm thinking about my tangent lines along my curve. Where can I find a slope? Where can I not find a slope? I'm tracing all my little tangent lines. I'm riding the wave. I'm surfing, riding the wave, right? Figuring out all your different little slopes. Okay, so now what I want to think about is looking at my graph. Where do I have issues? I have an issue at 1. 1 is a vertical tangent. It's a place where the graph suddenly becomes vertical. I also have an issue at, looks like x equals 3. That's a cusp. And I think that's it. So I have my intervals of differentiability, -infinity to -1, because -1 is that jump. -1 to 1, that's where we hit that vertical tangent. 1 until 3, because that's where we hit the cusp. And then 3 to infinity. So what's really important there is that I did include the -1 jump from before, and the question is saying, okay, identify where the graph is continuous, but not differentiable. Okay, well, it's continuous at 1, but there's a vertical tangent. That's what we learned about today. That's new information. We don't like vertical tangents. We can't find the slope there. Same thing with x equals 3. Can't find the slope there. We got a cusp. It's kind of an issue. Sad face. So that would be my answer to this question. Now, if you want to state the fact that, okay, well, also -1 is kind of a thing. -1's a big deal. We can't find the slope there either. Yes, that's true. Like, you can state that x equals -1 is a jump, but it's not really answering the question, because the question specifically says identify where the graph is continuous, but not differentiable. It is continuous at the vertical tangent. It is continuous at the cusp. It is not continuous at the jump. All right, look at that graph. It must be a Friday night. I am having way too much fun making this stuff. Go ahead and try this one on your own. It's asking about differentiability. Unpause when you're ready to see the solution. All right, here's our solution. Look at that thing. Look at this mess. Let's run through this whole thing and talk about why it's not differentiable at all these different places. Okay, so first of all, I have my discontinuities. My discontinuities at -3 for that hole, +3 for the jump, and +5 for the infinite discontinuity. That's old information. We did that in the continuity unit. We're just saying now that if it's not continuous, it's also not differentiable. So we include those in the interval, but now we got the new information. X equals -2. What's happening at x equals -2? Looks like a corner to me. X equals 0, we got a vertical tangent. X equals +2, we got a cusp. So this is a big graph. We got all 6 different types of places where we cannot find a derivative. Again, that means that we just cannot find a slope. Think about trying to ride the wave in all these cases. It would be very tricky to figure out exactly what your slope would be at any of those given x values. So we do end up with a pretty lengthy answer, and this one includes all of the different things that you guys have to look out for. The hole, the jump, and the infinite discontinuity, that all comes from the continuity content that we did back in quarter 1. The corner, the vertical tangent, and the cusp, that's the new information from today. The graph is continuous at -2. It's continuous at 0. It's continuous at 2. But it is not differentiable at those values. I hope this was helpful. I hope that you guys utilize this video. You watch it at least one time. That'd be good, and quite frankly, better than the continuity video. We all know that. Email your teacher if you have any questions. Thank you so much for doing your asynchronous work, not the night before the quiz. I'm so proud of you guys.